So I'm going to be talking all about pods today and a deep dive that I did and covering all the interesting and weird things that I've discovered. Before we get into that, I'll do a quick introduction to who I am. So I'm Marcus Noble. I'm a platform engineer at a company called Giant Swarm, where I work on release engineering, CI/CD, infrastructure, things like that, and like general Kubernetes development. I relatively recently started running a monthly Cloud Native newsletter where I do a bunch of updates on everything going on in the Cloud Native world called cloudnative.now. I'm a CNCF and a CVO ambassador, and at this point I've now got about 7 years worth of experience in the Kubernetes space. Over that time I started off as a Node.js full stack app developer and was responsible for testing out this new Kubernetes thing and see if it would work for our e-commerce product. Turns out it did, and I ended up running 3 different clusters for this team, moved into more of an R&D sort of role where I was building out tooling, best practices, and kind of things like that for a big multinational organization. And then more recently into platform engineering for customers, running and managing operating clusters at scale and developing operators and stuff for them. So I've covered quite a few different kind of roles within Kubernetes and saw a lot of different aspects of how different people use Kubernetes. When I proposed this talk and started working on it, my plan was to do a complete deep dive into everything about a Kubernetes pod. Now, this little tiny thing that we all use within Kubernetes, I thought, this would be good. I'll cover everything. My first draft was about 100 slides, took over an hour. I don't think you all want to stick around for an hour for this talk, so I refactored it a little bit and I pulled out the weird things, the interesting things, the things that made me go kind of, what the fuck? There's some interesting aspects, and we're going to cover a lot of those today. So let's start off with what is a pod, just so we're all on the same page. I assume majority of the people in here have used Kubernetes at some point because you're at a KCD, and as such you've probably touched a pod at some point. But let's have a look at what one actually is. According to the official definition, pods are the smallest deployable unit of computing that you can create and manage in Kubernetes. Now, there is obviously a layer below that, which is our containers, but the pod is the smallest manageable unit that you can deploy on its own for compute. So, the smallest deployable unit of computing. So this is a wrapper around our containers or our WebAssembly functions, things like that. And as I said, it's a wrapper around one or more of these. It is managed by the Kubernetes scheduler and is assigned to a specific node at runtime, depending on the various specifications that it's got. All the workloads running within that pod, so all those containers, they share the same runtime context. So this is your Linux namespaces, your C groups, your network, that kind of thing. They are designed to be relatively ephemeral and disposable. With a very few exceptions, pods are designed to not live forever. And for the most part, they are immutable, which kind of adds into this disposable and ephemeral nature of them. There's a few things you can change. So the image property on a container can change, the active deadline seconds, and the tolerations can be changed at runtime without recreating that pod. And as of 1.33, the in-place pod resize for your resources has graduated to beta, so you can also kind of use that as well and change the resources if you have enabled that within your cluster. But everything else you can't change. To be able to change any of the other things, you have to recreate it. But it's much, much more than that. And as I've kind of said, it's actually too much for us to cover in the time that we've got today. So I'm going to talk about the interesting, the weird, and the kind of surprising bits that I discovered while doing this deep dive, and the things that kind of had me going, why? What's going on here? So let's start off with containers. And the first thing I want to talk about is sidecar containers. These are enabled by default as of version 129. And they have the FeatureGate sidecar containers if you need to enable them before that. What's weird about these is they are what I call disguised as init containers. The way you define an official sidecar container is you create this init container with the property restart policy on the container, not on the pod, with the value set to always. There's no other value you can set. It's either doesn't exist or it's set to always. And if restart policy always, that is then a sidecar container. I don't know why they chose that way of doing things, but that's the way it is. For the most part, it's kind of like all your other containers. It keeps running after all your other init containers have started and runs alongside your main application containers. It supports things like readiness probes and things like that, unlike normal init containers that do not support those. So that's also a little quirk. And the termination of these is generally much harsher than your workload applications. So they will be sent a sig term followed very quickly by a sig int if they don't clean up quick enough. So don't try and do too much like cleanup logic within your sidecar containers because it's probably not going to survive. Yeah. Ephemeral containers. So these are also relatively new. These are designed for debugging. So these are containers that you don't define within your spec. The only way to actually add these to a pod is through a special ephemeral containers handler, such as the kubectl debug commands that you can use from the CLI. These are not supported on static pods, so you can only use these on your normal deployed pods within your deployments, whatever. And it's possible for these to target specific container process namespaces with the target container name property, or you can just have them within the entire pod namespace if you don't support this. On these, there is no support for things like ports, probes, resources, and lifecycles because they're not meant to live for long. They're only meant for you to drop into the pod, figure out why something's not going right, and then come out of it. But these are super useful when you're trying to figure out why your application's not working. You can drop into an existing pod in production without making any changes, and I don't know, have a look at your config files to make sure they're showing the right thing. Have a look at whatever you need, whether connectivity to certain things is working. Very useful. Pause container. So not many people that I speak to actually know what a pause container is, but I can guarantee if you're using Kubernetes, you're using pause containers. Every pod that you deploy has a pause container. You won't see it in Kubernetes, but it is there. The pause container is basically designed to bootstrap your pod. This is the thing that's responsible for setting up things like your C groups, the reservations, and those Linux namespaces that your pod will then use and shared with all your other containers. The idea for this is it's sort of like a parent container. So even if your app containers crash, this container keeps running and keeps a hold of those namespaces and C groups and stuff that has been set up at the start. As I said, these are not visible via the Kubernetes API. If you do want to see these, you've got to drop onto the node itself and ask your container runtime to list out the containers that it's running. So, for example, if you're using containerd, this little command here, ctr blah, 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 containers list, and then you'll look for these pause containers. Here we're using a renamed one that we use in Giant Swarm, but generally you'll see like a Google Container Registry image, whatever. And you'll have one of these for every single pod that you are running. Cool. So we talked about containers, so let's drop down another level and look at images. I want to have a quick word about image pull policy. So we're probably quite familiar with this, and there's 3 different properties that you can have with image pull policy. So if not present means that it will go and fetch the image from your container registry if the node doesn't already have it. Now this is the default value if you use a tag or a char other than latest. There is always, which will always go and fetch the image from the container registry. This is the default if you use the latest or if you omit a tag completely, which implicitly means latest. Now, what's interesting about the always tag is the cache mechanism within Kubernetes is actually smart enough that what it'll actually do is it'll ask the registry for the hashes of the layers for that image, and it will check if the node that it's running on has those layers already. If it does, it won't download them. So even if you specify always, it doesn't mean that it's always going to pull all that data again. It's just going to check if that data has updated, and if so, pull it down. And never, it will just hope that the container image is available on the node. You have to get it onto the node through some other means. This is generally in like air-gapped environments where you have some sort of other process that loads it onto the node specifically, directly via command line or whatever. But the kubelet here will not go out to a registry to try and pull it. It will just error out if the image doesn't exist on the node. Image tags, so using a char. Now, this is best practice for security reasons. The char is immutable. if you specify the SHA, you are getting exactly the same image each time. Things cannot change. Even if you overwrite the tag, that means the SHA will change. If you are using the SHA, it is usually useful to have it along with the tag, so humans can understand what version that is, because I don't know about you, but I can't remember a very long SHA, but I can remember 125.1. But what's interesting is if you do use the tag and the SHA, the tag's completely ignored. Doesn't use it at all. So that 125.1 there, that's not the same as the hash, as the SHA that I've defined. It will pull down the SHA. Doesn't mean that it's going to match to that tag. So be careful with that. If you're using things that automatically update your dependencies and you do have both the tag and the SHA, make sure it is updating both of them. Otherwise, you could end up with some surprises that you are not expecting. Great. Let's talk about runtime class. So runtime class allows you to have multiple different container runtimes in a single cluster. If it's unset, it will use whatever the default container runtime interface for your node is. So this is like container D or whatever it is that you have defined on your node. If it is set on your pod, you define it as runtime class name, and that has to point then to a runtime class CR within your cluster. That custom resource then has to define the scheduling and the handler. So the scheduling allows you to define what nodes are capable of this runtime. So for example, you may only have a subset of your node pool that has a particular runtime installed on it. So you can then use node selector labels to only run that runtime class on those nodes. And then the handler tells the node what binary is then going to be running your containers on that node. Now, it's kind of rare, I would say, to have, for example, containerd and cryo. So it's not really that often you will have multiple runtimes in that case, but where you will see it is when it comes to WebAssembly. So the way that we run WebAssemblies within our clusters is via a runtime class. For WASM, for example, WASM Edge is a runtime class for WebAssembly. Whereas you can then have your WebAssembly functions referring to this, and then all your other containers can then have the default, which will be your containerd, your cryo, whatever it is you've got defined. Cool. Let's talk about static pods. We've mentioned them very briefly in passing. Static pods are special within the cluster. They are managed directly by the kubelet and not by the API server. So these are directly on the nodes and not the API server. They are defined as static manifests, either as files in a directory on the node, which is then defined by the pod manifest path argument, or they can reference a URL using the manifest URL flag. That feels a little dangerous to me, so if you can, use it on the file system. But if you want to point to a web host and hope that it doesn't get hacked or whatever, be my guest. The kubelet will automatically try and create what's called a mirror pod for each of your static pods. Now, this is the pod that you will see when you do kube control get pods. So, for example, the API server, the example we've got here is kube scheduler. So this on the right is manifest. Yeah, right. Is a manifest for kube scheduler as a static file on the node. This is run by the kubelet. The kubelet will create this container, and then in the API server, it will create this mirror pod that is a read-only view of this static pod that it has created. You can't make any changes to it via the API server. The only way to make changes to it, is by changing the file on the directory or on the host. Because these are managed directly by the kubelet and not by the API server, they cannot reference any other resources. So you can't have, for example, config maps or volumes with a static manifest. You will see these used for things like the kube scheduler, the API server, those critical components that have to run first before anything else runs within your cluster. Right, lifecycle hooks. So there's a couple lifecycle hooks that I want to talk about. So these allow you to hook into the behavior of your containers, into the runtime of your containers. So these hooks are guaranteed to trigger at least once, but it is possible for them to run multiple times. So your hooks need to be aware of that and be able to handle it. There are two different hooks we're going to talk about. There is post start, which runs immediately after the container is created, but is not guaranteed to run after your init command has finished. So it could very well run before your actual code logic has finished setting up your application, so be aware of that. And also your container is not marked as running until your post start hook has finished whatever process it is doing, so that can't run forever as well. And there's also then pre-stop, which runs immediately before the container is terminated. So when you're, deleting your pod, scaling down your deployments, whatever, your pre-stop will kick in right before your container is actually killed. So you can potentially do some cleanup logic. You can do whatever it is you need to do in those scenarios. For both of these hooks, there are two different mechanisms that you can use. So there's exec, which allows you to do an actual command within the container. And then there is HTTP GET, which allows it to perform an API call from the API server, allows you to hit a port that's open in a container or whatever. On the right here, we've got a real-world example, slightly trimmed down, from the Cilium chart provided by Bitnami. The post start here sets up some IP tables changes when running in AWS ENI mode, I believe this was for. So this has to be run in a certain scenario. It does some things on the IP tables. And then the pre-stop here handles some uninstallation logic before it tears it down. I've also personally used this sort of thing in my home lab. I've used the pre-stop to copy some backup files upon scaling down. So like some database files, I've copied them over to a NAS and things like that. It's quite a nice way of handling that sort of thing. Cool. Let's talk about conditions and readiness gates. So probably all come across conditions in one form or another when looking at Kubernetes. So these are the things that you'll see within the status of your resources. But we're going to talk specifically about on our pods. The kubelet manages the following conditions for pods. It'll be pod scheduled. So this tells you when it has been assigned to a specific node. Before that point, it's in a pending state. It doesn't have any conditions yet. The pod ready to start containers is a beta feature. At least when I wrote this, I haven't checked since the latest 1.3 release. But this tells you when the pod sandbox has been created and the networking has been configured within your pod. Containers ready is when all the containers within the pod are reporting in a ready state. Initialized is after the init containers have completed, but your main workload containers may not be. And then finally, ready is when everything is ready and your probes against your containers are successfully passing. These status conditions may contain a machine-readable reason property, and or a human-readable message property. So the reason property is usually just like a error, blah, 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 whatever, some code. And then the human-readable one is hopefully something that an operator will be able to look at and go, oh, my application is broken because of this. Hopefully useful for debugging. Going on further than this is a thing called readiness gates that allows you to define your own status conditions. These are fairly rare used from what I've seen out in the world, but they've been around for quite a while. The main concern with these is you need an external application to process these, to handle these, and to do the updating of the status for you. So you need some sort of other operator running within your cluster. You define these via the spec.readinessgates array on your pod, and it is just a container type, and then it's a key to whatever the readiness gate is for that pod. The example I've got down here at the bottom is one from the AWS load balancer that does support enabling of readiness gates if you're using the ALB or NLB mode. What this will do is it adds a readiness gate to tell you that the ALB or NLB is ready and is reporting that it's able to serve traffic to that pod. So what it'll do is you'll define that readiness gate on your pod, and this external AWS load balancer application running within your cluster will then look out for those readiness gates, and once the status has been updated in the ALB or the NLB, it will patch your pod and add that status condition for you. it'll update that status to true as soon as the readiness gate logic is passing. So these allow you to kind of hold off on your pod being marked as ready until some external process, service, whatever, is also ready. Config. So configuration is quite a big thing within Kubernetes. There's a lot of things I could have covered here, and in my initial draft, it was a big part of it. We're going to cut that down quite a lot into just some of the weird things that I've come across. And we're going to start off with environment variables within our pods, within our containers. So you're probably aware that there are hard-coded environment variables, so you can give it a name and then a value. So for example, I've got a key here, the environment variable here with the name, and the value is world. What you can also do is have dynamic values within your environment variables that reference other environment variables. So the second one here, this greeting, actually references the other environment variable using this parentheses syntax. So it allows you to then reference to other ones that may be injected by some other services or whatever it is you need. There's also the downward API, which I really like within Kubernetes. I think this is a really useful API that you can leverage to populate your environment variable based on the values from other things within your pod that is often at runtime, often defined at runtime. So for example, you can reference things like fields from the metadata, so you can pass in the name of that specific pod. You can reference things from the spec. There are only specific fields you can reference, but things like the node name, for example, so you can know what node your pod is running on. You can get some things from the status, so the pod IP, for example, if you need that for any kind of communication with your other pods within a replica set. And also you can look at things like the resource limits that you set. So this is useful if your application needs to set the amount of memory that it's allowed to use so that it doesn't hit an OOM within your runtime. Because nobody likes getting OOMs, right? Cool. So we had a look at environment variables. Let's have a quick look at volumes. This is just a what the hell kind of example here. So you can have config maps and secrets, and you can mount them as files as volumes. If it's a config map, you reference it using config map and name. If it's a secret, it's secret name. I don't know why they didn't just use name for both, but it catches me out all the time. I can never remember which way round it is. It's very, very frustrating. Again, you can use the downward API. So we've got the same sort of thing that we see with environment variables, but you can reference things that then become files within a disk. So the path here becomes the file name, and then within that mount path that you've got within your volume mounts. And again, you can reference the same sort of thing. So you can have like all of the labels, all of the annotations, whatever, mounted into your container as a file that you can then reference within your application. Empty dir, I'm pretty sure you've come across these at some point or another. These allow you to have kind of an ephemeral workspace to store some files in at runtime that then goes away with the pod. One thing you may not be aware of here is you can actually define this medium and this size limit. So, the medium here, if you don't define it, it just uses disk space, so it uses some space on the host node. But you can set that as memory, which will then create an in-memory file system for you to use. Obviously, be careful that your node has memory to use and you don't use loads. And you can also set this size limit, which is especially useful if you are setting this to memory so that you don't use all the memory of your node and crash all your other pods, which will limit the amount of storage that you can have within this empty dir. Very useful to use this if you can. And then projected. So this is one that I hadn't actually come across until, hadn't actually realized I'd come across until I started digging into this. But this allows you to combine multiple sources, multiple volume sources into a single volume mount. So in this example here, we're actually taking two different config maps. So here we've got a web index, which has an index.html, and also a config map that is error pages, that is just a bunch of different error pages as HTML, so a 500, a 404, whatever. And we're using those as a single volume mount into our Nginx example here, so that we then have multiple HTML files from multiple sources, all within the same path within our container. And it's very useful for things like that. Again, these sources can use multiple different things, config maps, secrets, things like that. One thing that you probably haven't used yet, but it may be something that comes up more in the future, is the ability to use OCI images as volumes. So these were introduced in version 131 as an alpha. They are beta as of 133, but they're disabled by default. These allow you to mount an OCI image as a volume within your container. Secrets handling is done the same as pulling images, so you can provide an image pull secret. To be able to use this, the container runtime needs to support it, which is why this is not enabled by default yet. So Cryo and Containerd have some initial support for it, but it's still being worked on. But this, I think, will be quite useful, especially for a lot of AI folks that are using it, that are using Kubernetes for their AI stuff. You'll be able to mount some of your models from an OCI image into your containers and things like that. I think that's going to be quite cool. Cool. So let's move on to scheduling. And to start off with, I'm going to talk about resource allocation. So you've probably come across requests and limits. These tell Kubernetes how much usage of our hardware our pods are allowed to use. Now, this is going to be a very brief overview because there's a lot I could talk about here, and yeah, it could be a whole talk in and of itself. Requests are the minimum resources free on a node for it to be scheduled. So if a node doesn't have at least that much resources available, a pod will not be scheduled to it. And then limits is an enforced amount of resources that a pod is allowed to use at runtime on that node. Depending on whether it's CPU or memory, the effect of hitting that limit is different. So with a CPU, if you hit that limit, you end up getting throttled, so you can't use any more, but your application keeps running. It's just slower. Memory, if you hit it, is then enforced by the kernel, and you will get an OOM termination, and your pod will restart. Your container will restart, sorry. The reason I wanted to talk about this is, again, quite useful for the AI folks. You can actually have custom resource types on your resource requests and limits, and you will see this with things like the NVIDIA driver, and as well with the AMD one, I believe. You can define this custom one, which is here like nvidia.com/GPU, and define how much of a GPU your pod can request and can be limited to. There's a few caveats here. The requests and the limits have to be the same, at least for this NVIDIA one. And you cannot specify requests without limits, at least for this GPU resource. So it's best to define them both and have them both the same. But you can then implement your own ones as well if you have something else that you may want to request resources based on. I don't know what you might come up with. And then finally, as of 132, a new alpha was introduced, again disabled by default, that allows for pod level. That allows for pod level resource requests and limits. So up until this point, they've been defined on a container, and then kind of added together to then work out the amount used for the pod. Now you'll be able to actually define it on the pod itself. Now, why this is useful is a lot of the time your init containers, for example, may need quite a bit of resources to start with, but then nothing kind of after that, and then you kind of have to artificially inflate them and stuff like that. Or maybe it is a case of one of your containers has high at one point, and then the other container has high at another point, so you don't necessarily need double the amount, that kind of thing. So if you know, overall over your entire application, kind of how much memory and CPU the entire thing's going to need, this is a much better way for you to be able to define it, and will become more default in future releases of Kubernetes. So keep an eye out for that. And just a quick note on that, the container limits and container resources, the container level requests and limits will override the pod level ones, so they'll still be able to be defined as well. Right, let's have a look at node assignment. So the thing I want to talk about here is something that I wasn't really familiar with until I looked into this, which is topology spread constraints. So I'd looked into things like affinity, anti-affinity, things like that. I've used those quite a bit, but this was a new one to me, and this is quite an interesting, not necessarily well understood API from what I've gathered. This allows you to define different worker zones within your node pool. So you can define one grouping of nodes as a particular zone, another grouping of nodes as a different zone, and you can then try and spread your pods across them using this spread constraints. And the way you do this is you define a skew, which is the number of pods in a topology, a group, minus the minimum pods in any of the topologies, any of the groups. This allows you then to make sure that you don't necessarily have the same amount in each topology group, but you are not going to unnecessarily balance into a particular set of groups, for example. What's worth knowing about this is there's no guarantees that this constraint remains satisfied. So if pods are removed due to scaling down, this logic doesn't kick in. It's only when scheduling of the pods onto new nodes. So it is possible that you could still end up with a skew that you didn't expect because all of your nodes were removed from a particular topology group for whatever reason. But these can be used in collaboration with other assignment strategies like your affinity or anti-affinity. Cool. Scheduler logic. Priority and preemption. So one of the important things about Kubernetes is that you run lots of different workloads in here, but some things are more important than others. Generally speaking, things that we run in kube system are much more important than things we run in default, for example. The way that we can have control over this is using these things called priority class. So priority class is a resource that we can define. We give it a value, an arbitrary value, a number, whatever we define. The higher the number is, the higher the priority that is compared to the other priority classes. We then define a priority class name on our pod, and it will use that priority class. This is then used at runtime when scheduling to determine the ordering of things getting scheduled. So if I have two pods coming in that need scheduling at the same time, and one has a higher priority class to the other, that one gets scheduled first. And if there's a queue, things may shuffle around a bit, so the higher priority ones are scheduled before the low priority ones. The preemption policy can be set on the priority class. This determines whether other pods of a lower priority are to be removed or not based on this priority ordering, and to whether the higher priority ones should basically take over space on a node or not. I just found this interesting. It's possible to have alternative or multiple schedulers in Kubernetes, so you don't have to use the built-in default Kubernetes scheduler. You can define your own if you want to. I'd be very interested to know why you'd want to and what problems that is solving. That'd be very interesting to hear about. So if you have any, I'd love to hear it. And this is just handled by setting the scheduler name on your pod to whatever it is. If this is set to anything, the default scheduler doesn't do anything with the pod and hopes that something else comes along and sets the node name property on your pod. If nothing does, it doesn't get scheduled. And finally, I'm going to talk about everyone's favorite topic, which is networking. Networking in Kubernetes is very fun, and I'm going to talk about DNS, which I'm sure you all love very, very much. Usually, depending on the DNS mechanism that you're using within your cluster, so for example, core DNS, each pod will get a custom A record defined to it, which is usually, at least for core DNS, the IP of the pod .namespace.pod.cluster.local, or whatever you've kind of defined some of your defaults to. But this can be overwritten. For example, a pod's host name is set to its metadata.name. By default, but it can be overwritten if you specify spec.hostname, for example, or spec.subdomain. So for the example I've got on the right here, I've set my demo and example, and that will end up being mydemo.example.default.service.local. This is what the pod itself will see as its host name. What's interesting about this is core DNS doesn't know this. It ignores this, and everything else within your cluster will not resolve that unless you have specific logic to tell it to. So the rest of the things within your cluster will still use the 172, etc., etc. It is also possible to add additional entries to your hosts file within your container if you specify this host aliases. So this is an array of IP addresses and then host names. So if you want to manually define your DNS entries, here you go. DNS policy is a interesting spec. So this allows you to define how DNS is configured within your containers. And there are 4 different values you can have here. There is default, which is not the default. There is cluster first, which is the default. There is cluster first with host network, and then there is none. Now, The reason default is not the default is because this is actually the default of the node, not the default within the cluster. And then cluster first is actually whatever is defined within your cluster. So this is actually the default. Naming's hard, right? Cluster first with hostnet is what you want to be using if you are using host networking within your pod. And then if you define none, you have to define all of the DNS yourself on the pod. So for example, you have to define the name service to use, which is a list of up to 3 IP addresses. You have to define the searches that will be used, and then you have to define the optional options. So for example, the example I've got here will create that resolve file within your container. And that is it for me. That is all the weird and wonderful things that I found when doing a deep dive into pods. I hope you found this interesting and head-scratching as much as I did. If you have any feedback, I'd love to hear it, and thank you very much.